Well, we just wanted to say hello to everybody. We are picking up in Chapter 2. And here's something wonderful. Last year in Calculus BC, you studied slope fields. We're picking up with them once again. We're going to refer to them as direction fields. Some classes refer to them in that regard. But we'd like to get through this quickly and get you some time to work today. Imagine that we have a differential equation. First order, dy dx is equal to some function of x and y. So you could have x and y terms on the right. Let's just say we cannot find a solution. If we cannot find a solution, and by the way, the rest of this chapter, we're really going to look at different methods to do that. And even for the rest of the year, of course, we're going to be venturing off. But if you can't get a solution, you could at least get a slope field, a direction field. Remember that dy dx is the slope of the tangent line. So if this seems like you would have been able to do this even if you were absent today, how delightful that that would be exactly the case. You did this last year. Let's just say that dy dx is equal to 2x. And then we also have an initial condition. And we've got the initial condition y of 1 equals 0. But tell you what, let's go ahead and make ourselves a little grid here, an xy axis. And, just how far out you want to go can be a matter of just catching the general pattern a lot of times. Let's just say that we were going off in the x direction between 3 and -3. We very well could venture off 4 and -4. But regardless, as we're looking at this differential equation, dy dx, the slope of the tangent lines are only dependent on what coordinate? The x-coordinate. So in other words, hey, if I ever wanted to know the slope of the tangent line at a given point, it's completely independent of the y-coordinate of the point. Here we could say whatever x-coordinate we have, multiply it by 2. So look at the y-axis here. Every x-coordinate here would be 0. So my goodness, double 0 and you still get 0. Look at that. I've used a different color. How about at 1? What would our tangent line slopes look like there? When x is equal to 1, dy dx is going to be a positive 2. So it might look more like that. I guess what I'm trying to show you is that you should get all of those tangent line slopes to be the same. How about at -1? If I were at x equals -1, all those would be having tangent line slopes. At any point, we'd have a tangent line slope of -2. 2 times -1. So, wow, look at that. And we could keep going. What about when x is equal to 2? 2 times 2, we'd have 4. So we should see steeper. And in fact, right now, maybe I'm not making it steep enough, but just like so. At 3, we'd be at 6, even steeper still. Wow. What about -2? Well, I'd say, hey, how about -4? Well, you get the idea. Don't think I made those quite steep enough. And at -3, perhaps getting even more looking vertical, looking more and more steep. Well, you've done this before. You had to do this even on the AP exam. But the big question is, hey, what's happening when we've got this? Help me interpret that. Y of 1 equals 0. What does that tell us, guys? We've got what? What ordered pair on our graph? 1, 0. So what are we getting at? We would expect to see something like this and say, well, maybe, just maybe, we'd expect to see a curve that looks something like that. Just following that slope field. And of course, we could continue to direct that up. You might envision that it looks kind of parabolic, and just following that pattern. But we are containing the point 0, 1, 0 on that curve. And of course, there are infinitely many solutions to this type of a problem, but only one that is going through the point 1, 0 from what we can tell. We can solve this equation by separation of variables, and by the way, that's what we're getting into later on in this unit. Let's do that. dy dx is equal to 2x. We'll deal with the initial condition in just a second. Multiplying both sides by dx, there's no y term to bring over. We could now integrate, and let's see, what's the antiderivative of dy? We just get what? Y. How about the right side? What do we have? X squared plus c. But don't forget, we also have this initial condition of 1, 0. So I could plug in a 1 for x and a 0 for y. And very quickly, we find out that c is equal to -1. What are we really getting at? There's one particular solution to this slope field, to this direction field, that contains the point 1, 0. We have officially solved it. By the way, you would have been able to solve that last year as well. Well, we're almost done with the lesson today, thankfully. We're going to have to go and use technology. And here's the wonderful, wonderful thing, guys. When it comes to using the 89, the 89 can help us with differential equations, and in particular, it can help us draw slope fields, or as we just referred to them, direction fields. Now, just a moment ago, you saw that dy dx was equal to 2x. So let's get out our 89. And you know what we're going to do is first make a quick mention, and look, we can see some multivariable left over, can't we? What you want to do, of course, is go to mode. Okay, mode will take us to the graph menu. So press mode. It's just a little bit to the left of that down arrow, one row down, and then when it comes to our function choice, well, hit the right arrow and let's go down to number 6. Hit that right arrow. You have the option of going to differential equations. Hit enter. You can see I've now selected it. You have to hit enter one more time as if to say pretty please. And there you go. Now, thank goodness, we are ready to graph differential equations. How? Well, as always, we want to go to y equals. The 89 is a little bit different. The y equals is right above the F1 button in green, so let's hit green diamond F1. And you can see a very different menu. Very different menu. At the very top, it says T0 equals 0. Then it says y1, and it has a little prime there. By the way, that is a derivative. Here's the thing, guys, and please hear this. When it comes to entering in your independent variable in a differential equation, don't hit x, hit t. Use t instead of x. It's one of those little peculiar little twists that we had on the 89. As always, I think it's a good thing to type in multiplication as well. We had dy dx, that's our y prime right there. But tell you what, let's type in 2 multiplied to a t. And then you could hit enter. And we can graph Zoom Standard. If we went to hit second graph. Oops, sorry. And under F2, it allows you to graph Zoom Standard if it's not already there. Hitting F2, we have that choice. Would you look at that? You don't even need a program. Oh, when you hit Zoom Standard, evidently it altered it a little bit. That is unexpected. I had it graphed before. You can always change your window, but you can see what's happening. It's graphing your slope field for you. Now, wow, you hit Zoom Standard and it's changed that. I'm honestly a little surprised. Let's see if we have a Zoom Previous somewhere. I'll be honest with you, I'm having trouble finding that. You could always change the window if you'd like. Well, that's all well and good, but you might wonder, what about the initial condition? Now, what if you have a point 0, 3 and you'd like to throw that in? Now, I know that wasn't our original problem, but let's just say it was. Let's go to green diamond y equals. At the top, when you type in t of 0 equals 0, and you can go all the way up there, that 0 that I've highlighted over is the x-coordinate of your initial condition on the curve. It's the x-coordinate. So I'm going to type in, I'm going to leave that as a 0. Very often when you'd have a point like 1, 0 or something like that, you'd want to change that accordingly. So I'm going to leave that as a 0 for the moment, though. And then you can say, well, look, if you go down right below that, y sub I1, if you just hit enter right now, you go down to the bottom of the window, and then you can type in whatever number you'd like a 3, for example. And then just looking at the screen, you can see the very top, t of 0 equals 0, so that means my x-coordinate is 0. My y1 value is going to be a 3. Let's see what happens if we graph that. Hit graph, green diamond, F3, and let's see what happens. Not only are you getting your slope field, but the calculator is also going to graph out what the curve would look like with that initial condition put in. So that can be especially helpful. And wow, I'm a little surprised to see the Zoom Standard changed everything else up. If you wanted to change it, you could always go to the window. Evidently, x min, we could make -10. And then you could even graph that again. And you can see what's happening with this initial condition. Then it would graph first one side and then the other, but altogether you would have the curve that satisfies the slope field but also contains the initial value. So, what else can we do before we wrap up? Well, what if you just had to make a slope field where there was a y involved? Notice what you have to do. I've written it at the very bottom. You'd go back up and you'd have your t instead of your x, but you must have y sub 1 in this form. This must be y1. Naturally, kids are going to say, how do you get y1? Let's do that real quickly. It's not that difficult. All you got to do is type in 2t, hit enter, go all the way to the right, say times y, and then you just put a 1 right after it. So that's a little strange to see that. The directions are just a tad different, but then if you were to graph it, you'd be able to get this new slope field, looking quite a bit different. You can see what that solution would look like, and it's going to graph the other half of it pretty soon, evidently. Or perhaps that's all it's going to graph today. Wow. Okay, so evidently it's just that one half, but it still says it's busy.